In this video, I'll be creating a simply supported beam. I'll put some UDL over it, or the uniformly distributed load over it, and I'll try and correlate the theoretical calculations with what comes by designing the same structure in STAAD. So this time I'm not just going into STAAD, but I'll try and give you the calculations in theory first and then the results in STAAD. So this is going to be an awesome lecture. You'll not only learn about STAAD, but you'll learn some tips and tricks of the theoretical calculations as well. So don't leave your seats on this one. Let's begin. Hi, I'm Kushal from #begin. And if you're new to this channel is all about creating some awesome content for you guys. This series is on STAAD Pro. I'm planning to divert a little bit into web development areas as well. If you're new to STAAD, consider joining my private Facebook group, which I've created for all the users out there so that they can come, share, collaborate, and just work upon their ideas, their weakness. So without further ado, let's dive into it. This is going to be a little bit long lecture, but it's going to be worth your while. So this is the simplest supported structure that we'll be recreating in STAAD Pro. As you can see, my structure has a length L and a UDL value, or uniformly distributed load value, of W kilonewton per meter. Now I'll later put these values to some numeric values and try and correlate with the values which STAAD Pro gives us. So we'll be talking about three key parts here. The first would be the reaction values, which is very simple in this case. The second is the shear force diagram, and the third would be the bending moment diagram. So let me start off with the reactions first. So before calculating anything in a structure, there is one thing you need to understand, that a structure is at rest. This is a very important thing to understand. It's a small thing, but if you don't get this point, you won't be able to use all those equations which you see around you. So the structure is at rest, which means that at every point, all the forces, internal, external, are in equilibrium. That is, they calculate out to be zero. Otherwise, they would be moving. Hence, we talk about the case of static equilibrium. So static equilibrium says that any point on this structure will have a sigma f x value to be 0, sigma f y value to be 0, sigma f z value to be 0. Similarly, at every point, sigma mxy, sigma mxz, or sigma mzy, these are 0 as well. Now in a simple nomenclature, we call mxy as sigma mz, we call this as sigma my, and we call this as sigma mx. So we have our grid system something like this. So this is the z, this is the x, and this is the y. Now since our structure is in the xy plane, so we have our structure something like this. So none of the forces are coming in this z direction. So in a usual 2D case, what happens is these values are taken out of the consideration because nothing is on the plane zy. So this goes out of the picture, and nothing is along the plane xz. So this goes out of the picture as well. So what we are left with are these three equations. That is fx equals to 0, fy equals to 0, and mxy or mz equals to 0. Now one simple thing why we call it as mz, this comes from the right hand rotation rule. So if you just fold your fingers along the direction of the moment, so for example, all the moments we are talking about in the xy plane are either in this direction or in this direction. When you fold your fingers in this direction, so wherever your thumb points, that is the direction of, or the nomenclature we give. So in case of mxy, if we rotate our fingers along this plane, our thumb will be either pointing out towards z or it will be pointing inwards towards z. So in either case, we call it mz. So this is where the mz comes into picture. So once you have this theory clear or have this concept clear, we can move on to finding our reactions. So on my fresh page, I'll need to find my reactions. Now to find my reactions, the concept is very simple. I'll take up any point and I'll try to recreate all the three values. So my first equation is fx equals 0, the other is fy equals 0, and the other is sigma mz equals 0. So using fx, since there are no forces in this or this direction, the fx equals to 0 is again gone. So I'm just left with fy equals to 0 and mz equals to 0. So let me give these reactions as, say, RA, and this I'll call as RB quickly. So if I take this beam as a whole, all the forces on this beam are in equilibrium. So if I talk about the beam only, and I'm taking the upward forces as positive, so I have RA going upwards plus RB going upwards, but I have this UDL coming downwards. So the value of UDL is minus, it's W per unit length and the total length is L. So minus WL equals 0. Now this is using the condition of sigma Fy equals 0. Now if I talk about the beam again, and I'm using this moment command, I'm taking anti-clockwise to be positive this time, taking sigma mz as 0. So I'll take up any point. For example, if I take the rotation about this point, so along this point, RA does not have any moment to create. So RA into 0. Now RB is going to be creating a moment in this direction, which is the anti-clockwise. So it is positive RB into the length or the displacement or the arm length is L. WL, the total load on this is W into L, and this is creating a moment in the clockwise direction, which is WL into L by 2. So this is WL into L by 2 equals 0. Now if I equate it, RB comes out to be WL by 2. And if I further actually calculate, the RA will also come out to be WL by 2. So these are my reactions. Now there was obviously an easy method of doing it, just because it's symmetrical and the total load is WL. So these would have been half of it, and hence you would have got WL by 2. But I wanted to show you how the reactions are calculated. So my first part is done. The reactions come out to be WL by 2 and WL by 2. The next is the shear force diagram. This is basically the diagram of Fy and Fy in the internal points of the structure. So I'll be talking about all the internal points, which value of Fy is coming. So in order to create the shear force diagram, what I need is to get Fx at an arbitrary distance. So I'll just create a section at some distance, say X, from the point A. So this is point A, this is point B. These values are WL by 2 and WL by 2. Now what I'll do is I'll just take this section away. So I'll create what is called a free body diagram. So this is a FBD or free body diagram. What I have with me is the reaction which I already calculated, and at this point I have some hidden values of Fy and Mz. So there are some internal reactions obviously which would have developed. So if I take the arbitrary direction of the internal force, say Fy, to be going up, as well as the moment being anti-clockwise as Mz. Now these are internal values, mind you, these are not external values. And this section has a distance of X. So the total load on this is Wx. Now what I need to do is find the values of Fy and Mz. Once I find the value of Fy in respect of X, I can get a graph. Obviously, the same goes with Mz. So I'll first calculate with Fy. In order to calculate with Fy, I again have the concept of static equilibrium. Now the static equilibrium told me that if the structure is at rest, a part of the structure would obviously be at rest. Now this is a part of that structure. So the total loads on this would be such that they come into an equilibrium. So if I try and recreating this FBD beam and I take the value in the positive as in the up direction as positive, and I'm trying to create the sigma of Fy, this should come out to be 0. So if I try and calculate it, all the above the forces which are going up are the first force is WL by 2. So WL by 2 is in the positive direction. I'm taking Fy also in the positive direction, and my Wx is in the negative direction. So minus Wx. The summation of this should come out to be 0. Now if I calculate, my Fy comes out to be Wx minus WL by 2. So this is my Fy value. Similarly, let me create the value of Mz and then get back to the graph. So using the same free body diagram again. So I have my free body diagram beam again, but instead of evaluating the equilibrium in the y direction, what I'll be trying to do is calculating the rotational equilibrium. Since the structure is stable, so it is obviously a part of the structure is also not rotating. So in this case, I'll take my anti-clockwise to be positive and I'll try and do Mz of the whole free body as 0. I'll take any one of the points. It's better to use this point. What this will do is it will cancel this out, so I wouldn't be having to calculate two values. One would do. So taking it at the point X, what we get is firstly, so WL by 2 is trying to rotate this in a clockwise direction. So this is minus WL by 2 into the arm length is X. So this distance is X. Wx is trying to rotate it in the anti-clockwise. So plus Wx into the distance is X by 2. And finally, Mz I have taken in the positive or the clockwise anti-clockwise direction. So it's positive Mz equals 0. Now if I calculate, Mz comes out to be WL by 2 into X minus Wx square by. So I have my two values ready. So let me break these down into graphs. My first is Fy is Wx minus WL by 2. Now it's very easy to understand. The profile of the graph is governed by the order of the unknown. So in this case, the order is 1. So the profile is going to be linear. Now since the profile is going to be linear, I need 2 points to create the profile. So I'll take the first value at X equals to 0. I get the value of Fy as WL by 2. The second is I can take it at L. So I'll get I get at X equals to 0, I get minus WL by 2. At Fy at X equals to L, I get the value as positive WL by 2. And finally, if I try to check the value at L by 2, I'll get the value of Fy as 0. So my graph is going to be very simple. This is the point L, this is the point 0, and this is the point L by 2. So at 0, my value is minus WL by 2, and in this direction it is positive WL by 2. So my graph is something like this, the value being WL by 2 and W minus WL by 2. So this is my graph of SFD. Now this will also depend upon the convention. Some people consider their shear direction to be in the negative direction. So in that case, the SFD is reversed, but the profile remains linear and the values at the end remains same. The second is Mz, which was WL by 2 into X minus Wx square by 2. In order to get the profile, again, I'll need the order of unknown, or what we call X. So order is, as you can see, 2. So this is going to be a parabolic profile. Again, since this time it's not linear, it's parabolic, I'll need at least 3 points. So I'll do it for x equals to 0, and you'll get the value of mz being 0. If you go to x equals to L, my mz would again be 0. And if you go to x equals L by 2, my mz would be WL square by 8. So if I create my graph at L, at 0, at L by 2, my graph would be something like this. This value being WL square by 8. So this is my bending moment diagram. So you have done the theoretical part. I hope I made it easy and not difficult. I know my handwriting is very poor right now. I'm just getting used to this notepad. Let's get back to STAAD Pro and try recreating the model. I'll double click on STAAD Pro to launch the software. I'll click on create new project. I'll give this the name of simply supported. I'll copy the name and I'll quickly paste it. I'm leaving my length units as meters since I'll be using meters, and I'll leave my force units as kilonewton as I'll be requiring that too. So I'll click on next. It's asking me, do I want to create a path? Yes, I do. And I'll start with the snap node beam. So this is where you start up with the snap node beam. So I'll just click on finish. And as you see, I'm in my snap node grid area. What I need to do is create a beam. In my theoretical case, I took the length as L. In this case, I obviously have to take a numerical value. So let's go with a 10-meter beam. This is simply an example, so it doesn't really matter. I'll just click out of the snap node beam since I have my beam ready. I'll just go to the front view so that everything looks perfect. Now I will go and just give it some properties. So the first I'll just give it a simple rectangular face. So I'll give the depth to say 0.75 and the width to say 0.3. It doesn't really matter because we are not going into the deflection part. The deflection part would require the values of EI, which is the elasticity, and moment of inertia, which will of course depend upon the area of cross section or the area in general. But since we are just going for the shear force diagram, the bending moment diagram and the reactions, those values are independent of the material properties. Those are just dependent upon the geometry, the supports, and so on. But since in order to create or analyze a structure, I need to have some properties assigned to it. So I'm just going with the default values. I've created one video on how to create user-defined properties. You can go and check it out. In this case, I'll just use my assignment method being a cursor to assign. I'll just click on assign and I'll assign this property on my beam. I'll just click on assign to get back. Now the next thing is to create supports. So I'll need two kinds of supports. The left side is pinned. So I'll need a pinned support. So I'll just click on pinned. I'll click on add. The second type of support is one side being roller. So I'll just create. In this case, I'll go to enforced butt. So in a simple roller support, what we have is, I'll take you to my notepad quickly to show you. So let me quickly show you what a roller support does. So if I have, say, a roller support at one of the ends, and if I get some force on this direction, what it is doing is not offering any resistance in this direction. So there is no resistance in this direction. However, when this point is trying to go down, this is offering some resistance. So it is offering some resistance in the Fy direction. However, it's not giving any support in either the Fx or the moment. So this point is easily turned. So it can rotate around this point. So Mz is not available. Fx is not available. Only Fy resistance is available. So when we are going to our STAAD Pro and creating the structure, I'll just quickly go to my STAAD Pro. In this case, I'll need to release a few things. So my Fx is released, my Fz is released, my Mz is released, my My is released, and my Mx is released. It is only offering me any resistance or any true resistance in the Y direction. So I'll just click on add. Now my S2 support, the first support is the pinned support as per my diagram. So I'll just click on this, use cursor to assign, click on assign and go to this point and click on it. So I have my pinned support ready. The second is my created roller support. So in this case, I'll just click on it, use the cursor to assign and go to this point. So I have my simply supported beam ready. I'll just click on assign to get out of it. The next is giving some loads on it. So I'll just click on the next part where it says load. So as you saw, I'm moving in the top to bottom direction. I've created an entire video on this, on which sequence to follow or which is the best practices used by professionals. You can go and check it out after this video. I'll just quickly create a load case. I'll just click on add. I'll leave the default title as it is. I am not much interested in that for now. I'll just click on close. You should do your documentation properly, but since I'm trying to keep this video as short as possible, I'll just go with the default name. I'll click on add to create some loads inside it. Now my load is going to be a member load and it is going to be of some value of UDL. So let me take the value as a -5, negative being in the downward direction. So I'll just click on add and I'll click on close. So as I said in one of my videos, the way of giving any properties or any loads, it's divided into two parts. It's for the first is actually creating that load and the second part is assigning that load or the property. So this load is not yet assigned. You can make that out by seeing a question mark here. So I'll just click on this, use cursor to assign, click on assign and I'll click on this. So my loading is assigned. Now the next process which remains is giving one analysis print command. I don't need to see the output values, but if I did, I could just click on all, click on add and click close. So I'll just get all the outputs. By the way, I'll be going into the post-processing mode, so I won't be needing all those. Design is ready for analysis. I'll just go to analyze and run analysis. So my analysis is done. I am getting 2 warnings, but I'll keep these 2 warnings for a separate video. These warnings are just warnings. They are not errors. So I'll talk about these warnings in a separate video. I'll quickly go to my post-processing mode from right here. I'll just select go to post-processing mode and I'll click on done. I'll just select my load case number 1. I'll just click on OK and I am into my post-processing mode. By the way, if you're not in the post-processing mode, just follow this top menu and click on this post-processing after your analysis is done to get into the post-processing mode. In my case, the first thing I need to check is the reaction. So for reaction, I'll need the values at the nodes. So I'll just click on nodes and I'll click on reaction. Now my reaction is coming out to be in the y direction to be 25 and 25. I'll quickly go back and you see my reactions were WL/2 and WL/2. Now in our case, I have taken W as 5. I'm assuming it to be in the downward direction, so it becomes positive, and I've taken L as 10. So RA is 5 into 10 by 2. And RB is again 5 into 10 by 2. This comes out to be 25 and this comes out to be 25, both in kilonewtons. So if we go back to my STAAD, you can see the values are 25 kilonewton each. So my reactions are correlated. Now the next thing is to check my shear force and bending moment diagram. In order to get the diagrams, you'll need to go into the beams or the beam aspect of it. So I'll just click on beam. And I'll go to my graphs. Once I click on graphs, you can see my MZ is popping up and my FY is popping up. So FY is the shear force diagram. As you can see, it's a linear shear force diagram with the values being -25 and 25. This is just reversed. Some conventions take shear force in one direction and some take in the other direction. The key point is getting the value of the shear forces. So in this case, it's linear and at the ends, it's 25. So let me go back to my notepad, and if I see at the end points, the values are WL/2. Now WL/2 is the reaction, which comes out to be 25. So this is 25 and 25 each. And at the middle, it's 0. And as you can see, it is correlating. At the value of 5, it is 0. The next was MZ. In our case, we have taken the sagging moment to be positive. STAAD Pro takes it as negative. It doesn't really matter again. You just need to have the values of the moments. This is a convention. So you can call this hand left or right, it doesn't matter. And you can call this left or right, it doesn't matter. The purpose, it needs to be solved. And when it comes to structures, all we need is to get those force values and to create materials of specific strength so as to resist those values. So at the middle, you can see the value is 62.5. Let me correlate it with my value. the value at the center was WL square by 8. So this was 5 into 10 square by 8. If you calculate it, it comes out to be 500 divided by 8, which comes out to be 62.5 kilo Newton meter. And at the ends, it's obviously 0 and the profile is parabolic. So as you see, the center point is 62.5, the ends are 0. So there you have it. I have both analyzed my simply supported beam from a theoretical point of view using the calculations. I just showed you a bit of a glimpse into how you should go about creating a structure or what calculations are needed. This was a very, very beginner step, and I also correlated it with the actual STAAD values. Again, the conventions of shear force diagram and bending moment diagram depend from person to person, in fact, not even country to country. But as you see, STAAD takes the sagging moment as negative. We usually take it as positive. And there you have it. So if you liked this video, please do hit that thumbs up. If you found any problems, do give me a comment below. Also, if you're not subscribed, please do so, and do not forget to hit that notification bell. I'm trying to put out content almost every day these days, and it's your love and support that keeps me going. So that is all from this session. Thank you for watching, and I'll see you on the next one.